Hey, how's everybody doing? I hope everyone had a wonderful weekend. This video is linked on Power School on Unified Classroom on our new page called Covalent Bonding, and you'll find it under the very first discussion that says Tuesday, March 17th. There's a link to this video. It'll be a YouTube video, and it's hopefully going to be available for you guys for a while so we can learn a little bit about covalent bonding tonight. So um, I'm going to start by basically giving a little presentation on um, covalent bonds, what they are. So hopefully this will be a good way to learn about this. So let me start out the presentation here. And you have this presentation on Unified Classroom. It's on a normal spot on the left side of the screen. So just you can follow along. You can listen to this video. Do whatever you have to do to hopefully learn about this content. If you have any questions, please know that you can also, or you can always add those to the discussion posts. I'll hopefully answer those in real time. But also, if you have another question, you can always email me and I'll get back to you as soon as possible. We did begin this class hopefully with a live meet using Google Meet. Hopefully that worked out pretty well. And we will be doing that periodically over the course of the week, as long as we're doing this. So let's start out with this, these notes here. We just did a whole section on covalent or ionic bonding, where we transfer electrons from one metal to a non-metal, and it forms a positive and negative ion, and those things bond together to form an ionic bond. We're going to start now with a little bit of a discussion on what the other type of major type of bonding is. That's covalent bonding. This is very much an introduction. We'll see a couple of different examples of this in action and how it works. And then from there, we'll go into how to draw these out using Lewis dot structures, what the actual geometry of these molecules look like. We're going to name them again. There are totally different rules. And hopefully learn a lot about covalent bonding in the next week or two. So let's start out with some basics about covalent bonding. Covalent bonds always start with nonmetals. So if you think about your periodic table, the nonmetals are above the staircase. And there's not that many of them. As we've already learned, most of the elements on the periodic table are metals. Covalent bonds are only the nonmetals. So that's all you have to worry about. And nonmetals have a very high electron affinity. That means they have a very strong love for electrons, if you want to put it that way, which means that each nonmetal involved in the bond, because it's only between nonmetals, wants to take more electrons. They both want to take the electrons. It's not like an ionic bond where the metal wants to give away their electrons, the nonmetal wants to take it. It's totally different. Nonmetals both want the electrons, and that's going to create a situation. Since they both want them, they're not going to give them up very easily. So if two people don't want to give up something, the best solution is to share it. And that's what happens with covalent bonds. The electrons involved are basically shared by both elements involved in the bond. And this will then, if they're sharing these electrons, they're always trying to get enough electrons to obtain that stable octet, those 8 valence electrons that we talked about throughout the last couple chapters. So big point here, covalent bonding only occurs between non-metals. We will not see any metals in any of these compounds that we look at. And a word that we oftentimes use for any compound that is formed by covalent bonding is a molecule. You may have heard that word before, but we only use molecule, that word, to describe a compound formed by covalent bonding. Ionic bonds are not called molecules, so don't do that. Only call molecules covalent bonded compounds. So covalent compounds are molecular compounds for the most part. Okay, the way we're going to learn this is by looking at basically 7 different types of 7 individual compounds that we call the diatomic elements. And the diatomic elements, that word di means 2. So it involves 2 atoms stuck together, and they're both the same atom stuck to itself. And the 7 atoms or elements that like to do this are the following on the page here. So they're all nonmetals, and there's only 7 of them. There's hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. So we have 3 very common elements: hydrogen, oxygen, and nitrogen. And then we have the first four halogens on the 17th column: fluorine, chlorine, bromine, iodine. Those are 7 diatomic elements. Why are they diatomic? Because they basically form compounds with themselves. And they're covalently bonded together. They're going to be sharing their electrons. And that's what we'll be showing you in the next couple minutes. And all of these do this. And they're probably the simplest type of covalent compounds. It's a great place to start. So make sure you commit to memory that word diatomic elements. And I would definitely memorize these 7 elements that can do this: hydrogen, oxygen, nitrogen, then fluorine, chlorine, bromine, and iodine. So try to commit that to memory as best you can. We're going to start with the very simplest one. That's hydrogen. Hydrogen, I know, is on the left side of the periodic table. However, as we've always said, it sort of acts more like a non-metal most of the time. So we're going to consider hydrogen a non-metal just because of how it behaves. And since it's diatomic, 2 hydrogens are going to want to stick together. As you can see on this picture, you have basically those circles are representing the atom, but above it are Lewis dot structures. We've already drawn those. We know there's one dot for each H. That one dot signifies the number of valence electrons in a hydrogen molecule. And I think we know already also that hydrogen, unlike most elements, does not want an octet. It actually wants what we call a duet. It only needs 2 valence electrons to fill up that first shell. So as you can see, it has 1 dot. And the other hydrogen has 1 dot. Well, both of those hydrogens want to keep their electron, but they also want more electrons to get that stable duet in this case. So what happens is they basically come together like this, and they share those electrons. So if they both share, that the green one and the yellow one are both sharing the other electron, how many total electrons do they have then in the valence shell? That's right, they have 2. This forms a molecule called H2. And H2, here's H2 right here, is how we would write that. Hydrogen, there's 2 hydrogens together. Diatomic elements, basically, or molecules in this case, would be the element with the 2 behind it. So H2. And notice how even it came together, the actual electron configuration came together. Now that outer shell has 2 electrons in the opposite directions, even in that orbital. So that is how a covalent bond forms, basically. It has a full 1s subshell then. Full is good. Full is stable. It basically is mimicking the outer shell of a helium atom, which is a noble gas, because they all want to be like a noble gas. These two 1s orbitals actually overlap together, and that's what the actual bond is. So each atom, since they're sharing the other electron from the other H atom, acts like it has 2 electrons in it, because they're sharing. Both of them are equally sharing. This H is sharing the yellow one. This H is sharing the green one. So if we kind of cover up this H here, this H would have 2 electrons. If we cover up this H, this yellow one would have 2. So now they're both really, really stable. And that's kind of the basis of how covalent bonds work. Let's do it for some other ones. Let's do it. Actually, hold on a second. We call this, got ahead of myself a little bit there, one pair of shared electrons. This is a pair of shared electrons, we call it. Those 2 H's have a shared pair. That's a covalent bond right there. So wherever you have a shared pair, or more pairs sometimes, that is a covalent bond. So let's continue a little bit to see some other details here. You can sometimes draw, instead of drawing the 2 dots like that, you can actually draw a line in between the H's. That's very commonly done to signify that bond. So a line between the atoms shows the covalent bond between these 2 hydrogen atoms, that shared pair. Let's do it with fluorine. I mean, we kind of skipped a couple. We skipped oxygen and nitrogen. We'll get back to those later. But the fluorine molecule is another one of those diatomic elements. It likes to form a covalent bond with itself, basically. So let's look at a fluorine atom. There's 2 of them here. This is the Lewis dot structure. If you notice that it has 7 valence electrons, and so does this fluorine has 7 valence electrons also. If you draw the Lewis dot structures, then this 2p5 area, there's 5, and there's 2 here in the 2s. So in the second energy level, there's a total of 7 electrons. This one has the same thing. It's the same atom, basically. It has 7 valence electrons. Well, we all know they want to form an octet. And to do that, the easiest way to do this is to say both want electrons, is to share this lone. I mean, look at this. This is a little atom or element, or Electron that's kind of alone. It wants a partner, so it wants to bring it in here and share with each other. And basically, it's going to form this. It's going to come together just like the hydrogen did, but a lot more electrons going on. This F has a full valence shell then. It has 7 yellow ones and then 1 green one sharing with the other fluorine. This one has 7 green ones and 1 yellow one sharing with that fluorine. It has an octet then because it shared that electron. And that is so key to how a covalent bond forms. It has the octet. It always wants to be stable. Now, by sharing these electrons, each fluorine in this bond then has the valence shell of the nearest noble gas, which happens to be neon in this case. And that makes it stable. Noble gases are stable because they have an octet. Well, this fluorine, when it's covalently bonded to this other fluorine, also has that same stable octet that neon shares. And that's why we prefer to be like this, to be bonded with another fluorine. That's how that works. Now, since all the halogens have that same 7 valence electrons, they all bond the same way. So fluorine does it that way. Fluorine does it that way. Bromine does it that way. And also iodine. So those 4 all do the same thing. They have 7 valence electrons. And they share that 1 from the other one to make 8. That's the same exact idea. Now, obviously, they have bigger radii as you go down the list here. So slightly bigger atoms. But the same thing's happening in every single one of the valence shells. That happens with all those. So that's why those 4 form diatomic elements so well. So we have hydrogen, fluorine, chlorine, bromine, and iodine. Let's do 2 more. And then you'll understand pretty much what a covalent bond is. So far, all these atoms can form only one covalent bond, that shared pair of 2 electrons, one from one atom, one from the other. And then when they come together, they have that shared pair we call a covalent bond. We've only had 1 so far. Well, some elements can actually form more than 1. So our one that's more than 1 covalent bond, oxygen. Oxygen molecule is such a common molecule, makes it 21% of our atmosphere. You're breathing it in hopefully right now. Plants are hopefully giving it off right now so you can breathe it in. Oxygen is a fundamental molecule of our planet. Very important for life as we know it. Oxygen is a diatomic element. It will form a bond with itself. And we're going to see how it's done. Look at this oxygen here. Oxygen happens to have, you know where it is, on the 16th column, it has 6 valence electrons. So does this oxygen, because all oxygens have 6 valence electrons. We'll put them together, and here's what happens. So let's back up 1 there. See how we have 2 that are not paired up in our Lewis dot structure? Remember we drew Lewis dot structure, sometimes they're not paired up. Well, those that are not paired up want to share a spot, but one over here it's not paired up. And this one here wants to share a spot with this one over here. So when they come together, you actually have 2 shared pairs. That is very important. Each shared pair is a single covalent bond. So this one actually has a double covalent bond, 2 of them. We would write this O2 because there's 2 oxygens together. When you breathe in oxygen, you're breathing in O2. You're not breathing in 1 atom of oxygen. It's always connected with another oxygen atom, just like this, basically. So 2 pairs of electrons are actually shared, not just 1 pair, like the other 4 or 5 examples we saw. It's called a double covalent bond, or sometimes shorter, a double bond. And sometimes we actually write it like this, where it looks like an equal sign, but it's 2 lines together. So that signifies each shared pair, there's a shared pair, there's a shared pair, is 1 single line stuck together. So that is a double covalent bond. Each atom then has 8. 1, 2, 3, 4, 5, 6, 7, 8. It only has those 8 because it had to share 2 from the other one. It has 6 plus 2. This one here over here, 6 plus 2 equals our magic number of 8. And then overlaps down here too. You can see the orbitals actually will overlap then because they're sharing some electrons. Last type, the nitrogen molecule. Nitrogen is our last of our diatomic molecules. So we had hydrogen, oxygen, then fluorine, chlorine, bromine, iodine. Nitrogen is the last one. And nitrogen is going to form what we call a triple bond. Look at nitrogen, has 5 valence electrons. Both of them do. And with those 5, only 2 of them are paired together, right here. These 3 are alone. They're all alone. These 3 are all alone too. They love to be paired up. And what happens is they come together, And now we have 3 shared pairs. Those shared pairs basically form 3 covalent bonds, a triple bond. We would call this N2, not 2 nitrogen atoms covalently bonded together. 3 pairs of electrons are shared. You can see it on the orbital diagram right here. It's a triple covalent bond, and we absolutely draw it then. If you don't want to draw the 3 actual or pairs of electron dots there, you actually have it with these 3 lines together, a triple bond. Nitrogen is one of the only ones that can do this. Carbon can also form a triple bond occasionally. So nitrogen is going to be a very common one that can do this. This atom also then has a full valence shell, 1, 2, 3, 4, 5. 5 yellow ones, 3 green ones it's sharing. 5 plus 3 is 8. 5 plus 3 is 8 here too. Your math will never fail you. So if you can count to 8, you can do chemistry. So that is basically a triple bond. Let's talk about bond energy real quick. Now that we know bonds form, let's talk about the energy involved. And this is a little throw in at the end here before we get to our next topic, which we for tomorrow, Lewis dot structures. But let's talk about the bonding energy here. When you form a covalent bond, when all these things are happening, when these covalent bonds are forming with these valence shells overlapping, 435 kilojoules of energy is released every single time that happens, for a hydrogen molecule at least. And that I don't need you to know that number, 435 kilojoules, but that's released. Now, here's the cool thing. If it releases 435 kilojoules to form the bond, that's why when you form a chemical bond, energy is a lot of times released as heat or light. To break that bond, you have to supply 435 kilojoules to break that bond. This is actually called the bond dissociation energy. It disassociates the energy. The bond is an association between 2 atoms. If you disassociate it, it goes away. The bond breaks. So you have to provide at least 435 kilojoules to do that. Now here's kind of the key. The shorter the bond, the greater the bond energy. So the shorter the bond, the closer the bond is, the greater that energy is. So the single bond, that sigma bond, that single bond is the longest of all of the covalent bonds. So that means a single covalent bond, like for hydrogen, fluorine, chlorine, bromine, iodine, basically has the lowest amount of energy. So it takes the lowest amount of energy to break it too. So it's the weakest of the bonds. Triple bonds are the shortest, so they have the highest bond energy. When they form, they release the most energy. They also would have the most bond dissociation energy also. So obviously that means triple bonds are really hard to break. So they're really, really a strong bond. This bond energy is always positive. So if you're actually measuring it with some tools in the lab, which we're not going to do in lab, but if you would ever in the future, it's going to be a positive energy when you do the calculation for breaking the bond. It's that's because that's how much bond energy you need to break it. And the energy released, if you ever measure how much energy is being released, if we do the calculations, the energy is actually be a negative number. So if you ever see any information about energy given off or being used to break a bond, you're going to see positives and negatives. Positive means you're breaking the bond. Negative means you're basically creating the bond. You're forming the bond. Okay. So I hope that made some sense. Obviously, since this is a recording, you can watch it all day long. Forget about Netflix. You got Mr. Stam talking about covalent bonds, which I'm sure is so exciting. I'm going to quit this one right now. What I want you to do is obviously watch this and pay attention to the discussion on Unified Classroom, and we'll give you further instructions on what you're supposed to be doing with this information, how I'm going to take attendance, and also what you're responsible for this information. So I hope you have a great day. This is our first day of remote learning, and I will see you virtually somehow. Have a great day. Thanks.